When a vehicle is going through a turn, the outside wheel needs to run a longer distance than the inside wheels. A car solves this issue by having its wheels running at different rotational speeds. The wheels are totally separate or connected with a differential. For a train, the wheels are connected with a rigid shaft to be able to endure much higher axle loads than a car. If a train had cylindrical-shaped wheels, it would run off the track, as nothing would guide it along the track. You might think that this is the reason train wheels have flanges. These sit on the inside of the rail and could guide the wheels in a turn. But when a flange hits the rail, it makes a high, loud squeaking noise, and also endures a lot of wear. This is something engineers want to avoid, and that is why the shape of the wheel itself is important, and the flange is really only a safety mechanism. So how can this issue be resolved? The answer is that the wheels need to be conically shaped. They're a bit larger closer to the train and smaller on the outside. In a curve, they slide out a bit on the track. That way, the outside wheel has a slightly larger radius, while the inside wheel runs on a smaller radius. With these differences in radius, the outside wheel will travel further on one rotation than the inside wheel, making the turn. This works perfectly. But now look what happens when a set of conically shaped wheels runs along a straight line. You can see that a really small disturbance of the wheel set makes it wobble. As the wheel moves sideways, it runs a larger distance, and therefore starts turning the wheel set in the other direction. But by doing so, it overshoots its own correcting behavior. This overshoot is then corrected for when the wheel set starts moving sideways in the first direction again, overshoots again, etc., etc. So the correcting behavior, which was so suitable for going through curves, now induces this wobbling movement that we call hunting.